PhD student in my lab, finishing in just under a month. And he is the absolute expert in anything related to tools for multi-agent reinforcement learning. So it's a real privilege for you guys to have him present this work here today. Matteo, the floor is yours.
Yeah. Thank you, Amanda. Yeah, so just before starting, I have some Swiss chocolates here, and I will be asking a few questions, and there are some chocolates on the lines, so real reinforcement learning. Yeah, so the work I am presenting today is about tools, and it's part tools that we developed here in the university and part that were developed as part of PyTorch at Meta. Specifically, I divide into two, more or less 30-minute parts each. The first part will be about simulation and simulating multi-agent systems, and the second part will be about training. And for each part, I will introduce the library that we will use. There is a notebook for this lecture. I shared it yesterday on Google Colab, but if you haven't, please scan the QR code. Keep it open on the side, because later we will go through parts of it together. So it's good if you can follow along. Okay, so if we're ready, first part, simulation. So maybe already we can start off with one chocolate question. Why do we need simulation? Any ideas? Yes?
It's too slow to train a real world.
Yes? Speed? Yes? Can you think of other reasons?
Cost.
Cost? Other ones? Yeah?
You cannot mathematically prove it. You try to simulate a model.
If you cannot prove what?
If you cannot prove that something happens,
Yeah.
then you have to simulate it.
Yeah, all correct. And I will show you practically what this means. These are videos from our lab. You can see that they crash into the obstacles, they crash into the camera. So this is related to the cost. And the main reason that this is another video from drones. And yes, part of the reasons is this one. So it's very costly to train robots in the real world. It's time consuming because it takes a lot of time, and it's dangerous. It's very difficult to, for example, you can think of an autonomous vehicle that needs to explore, and it needs to know what it means to crash into a wall, but doing this in the real world is of course too dangerous and unfeasible. Yes. So let's assign the chocolates. Do you have any preference?
No. Thank you.
A preference? Dark?
Yeah.
Dark? I don't know if you have any darks. Yeah.
You're blazing through those, Jenna.
Yeah.
Okay.
It's also,
I think too generous. Too generous. Next one there will be only one right answer. But so deploying robots in simulation, on the other hand, is very fast, it's safe, and it's efficient. But there is one problem, right? Like if you're using a simulator, how do you go from the simulation to the real world? And this problem is called sim to real. And there are many different ways to approach this. One is to do it in 0 shots. So basically just train it in simulation and deploy it in the real world without thinking about it. This is what we do in these deployments. What we just did to make this happen is that we need to tune the simulator with parameters from the real world. And the other way is you can do fine-tuning in the real world, so a few shots. So you do most of the work in simulation and then the last steps in the real world. Otherwise, you can learn the simulator from real-world data as a kind of word model architecture. And you could also, at the other end of the spectrum, you can learn in the real world, like on the robots. And for each of these, I left a reference you will find later in the slides if you are interested. But also, what is different from single agent? And well, there are more agents, and this complicates things. But yeah, any ideas what is different from single agents? There are many reasons. So. Like, what are some aspects that emerge only when you have multiple agents?
anybody ever attend any of my lectures in the last 4 weeks?
Yeah.
The environment is affected not just by the actions of the agents you're controlling, but the other agents. In
Yeah.
It's an unpredictable way.
Yeah, exactly. If you are one agent, you also have to interact with others. From a learning perspective, like in terms of, like, you know, you go from a single MDP to a more complex formulation. I can start giving some examples. So these are some of the axes. They are not all the axes, but some of the axes that could be different. So now you have all these problems about information sharing. So in a single rewards, the single agent setting, you have like one reward, one state, one value, and so on. Now you can have either sharing rewards or non-sharing rewards. You could have like a global state or individual observations. You could have different done flags or the same done flag for all the agents and different value and estimation. Another paradigm that could be different is like, how do the agents interact with each other? Do they cooperate? Do they non-cooperate? Or do they compete? Then there is also physical heterogeneity, right? Do they have different capabilities? Do they have different sensors, actuators? And behavioral heterogeneity, like even if they have the same capabilities, do they have different behaviors? Then asynchronicity, which is something very important in robotics, which is like they might not be all synchronized in their interactions with the environment. And you know, communication, because if you have all these agents now, they could talk to each other, and you can use this as well to distinguish them. So really, by choosing like what you want about in each of these axes, it's always you create a very different multi-agent problem. So when people say multi-agent, it's actually a very, very broad domain of things, like the coffee machine choice problem. But there is one formulation to rule them all, which we have seen in the previous lecture, which is the partially observable Markov game. So, you know, just recap, you have these agents, they take actions, a vector, the vector of action goes to the environment, which outputs a vector of observations, and a vector of rewards are given to the agents again. This formulation is quite general, right? We have seen that it is every other formulation, like the DAC POM-DP, are a partial case, a specific case of this POM-G. So really, it can simulate a lot of types of games. And here you can see some type of games you can simulate, or you know, scenarios. When designing a simulator, you know, ideally you want to be able to simulate any POM-G. And already here, some simulators that exist in the literature just constrain to specific things. For example, are just that do DAC POM-DPs and DAC POM-DPs with identical homogeneous agents, and so on. So here is one first property of the simulator we will see, is that the aim is to be able to simulate any POM-G, so with all the physical heterogeneity, reward heterogeneity, and so on, that's available. But before seeing that specific simulator, let's see what are alternatives that you could consider. Of course, there is no one-fit-all solution, right? Every time there is a simulator, this is made with some assumptions, and you have to understand if these are the assumptions that are good for you. Here, there are some examples. For example, MA agent is made for simulating a lot of agents, but it's a grid word. Isaac Lab, it's an NVIDIA based on the physics engine from NVIDIA. And it's very accurate, but it's, of course, more costly. Mujoko is also a physics simulator, usually single agent for some locomotion tasks. There is Unity ML agents, which is based on the Unity game engine. Again, a very expensive but really accurate physics engine. And then Petting Zoo is just a collection of a few games. And Melting Pot is a thing by DeepMind, which is, again, grid word scenarios, very simple, but they're focused on cooperation for social dilemmas. So if you're interested in that, that's definitely a good thing to check out. Then the one we're going to talk about today is this vectorized multi-agent simulator, which is an open source framework designed to make multi-agent reinforcement learning. And it has two components, which is basically a physics engine written in PyTorch, and a set of scenarios. What it is that it is vectorized. So this vectorized we will see later a bit more in detail, but what it means is that if you're running on a GPU and the simulator can run on a GPU, you will pay the same price to simulate one environment or n environments, as long as they fit in your memory. So it allows to scale in the number of environments very nicely. Then simple, general, customizable. The idea is that you can implement your own scenario or play with the existing ones, and also differentiable. And it is not high fidelity, so the scope of the simulator is to simulate high-level multi-robot tasks. So we don't care about simulating each of the joints of with really like NVIDIA or Unity level accuracy, but we're more interested in the collective decision-making problems. It's not 3D, it's not turn-based, and it's not asynchronous. It's just important to know what it does not do. The structure is more or less like this. So you have 3 components. The interface is more or less what you see normally from an RL environment. So this normally has functions like step and reset, which just advance the state of the simulation. And this is what interacts with the outside world. So, it could be Gym, RLib, or other libraries. The core is just where the physics is. This is just, like the physics step, how you can compute the next position based on the input action and so on. And then the scenario is really the component that you implement when you create a multi-robot problem. So you have functions like make world, where you start putting all your agents in the world. You have reset world, which tells the world how to reset. You have reward, an observation function, and you can see that some of these functions map to the POMG. So reward, you will implement basically your reward functions. Observation will implement your observation functions. So the breakdown on how you create a scenario is very much following the POMG structure. And we will implement each of these functions in a second. But yeah, just an overview of some of the scenarios available. You can see there are 30 plus now, and there are always more. And people make their own, and not all the people just feed back to the library. So these are just the ones we collected. And there is tasks like football, like games, or collective transport tasks where the agents are joined physically with a constraint, or bio-inspired tasks like flocking or sampling of latent distributions, and so on. There are really many possible scenarios. And yes, this is just an overview of what we will see and what we will not see today. I won't go into reading all of this, but this is probably useful in the future. If you go back to the slides, you can see what's available and what's we did not see, but it's still available, and you can try to work on. Yes, so if there is no question, I can show you a bit how VMAS works, and we can look at the first part of the notebook. The first thing I wanted to show you is that, so here I'm just in Python, and this is just the VMAS folder. And we have this category called scenarios, like it's a folder with scenarios, and every file here is one scenario. And one thing you can do is that for any of these scenarios, you can right-click and you run it, and you can play the scenario. So you can, using the arrow keys, you can control 1 or 2 agents, and you can like reset the scenario. The idea is that when you implement something, it's very difficult to know if you did a good job or not. So the best way to understand that is if you are the agent. And if you are the agent, then it means that you will have the observation and you will take the actions with your keyboard. So here you will be fed, the observation. In this case, there are many, so it's very difficult to semantically understand them. You also see the reward, the total reward, the current done flag, and which agent you are controlling. And so when you're just coding up something on the fly, this is very useful to check if the reward makes sense. Like if I go towards the goal, does my reward decrease? And here in the specific case of football, you can also play the game. It's very difficult, but you could potentially try to prevent the opponents from scoring. And you can do this for any of the scenarios. So in the balance case, you are these agents under the rod, and you have to try to bring this up to the goal. And so on. And okay, maybe I'll show you the one we will code today, which is this one. So in this one, it's a navigation scenario that I want to see today, and it's basically where each agent is interested in going towards their goal. So you can see the agents here are the bigger colored objects with the little dots all around them. And their goal is basically to navigate to the same, to the small circle of the same color. So the green wants to go to the green, the blue to the blue, and the pink to the pink, and so on. These smaller ones are the goal. They are not collidables. They're just like landmarks. And then these black circles are just obstacles. And the agents need to avoid the obstacles, and other agents where they're going to the goal. And in order to avoid other agents, you can see there are these like little dots around with lines. These are like whiskers for a cat, and in robotics it's a LiDAR sensor. So it means that if these little dots detect something in their way, they will measure the distance to the object. So when two agents go near to each other, basically their LiDARs will perceive this. You can see that here, these dots basically perceive that there is another agent around. So it's a way for, it's a sensor where the agent can use to see each other. And we will have 3 types of embodiment. So you can see this blue agent is like holonomic. It can move into the anywhere. And the same goes for the orange one. And then we have the green agent, which is a differential drive robot. So with one action, I can decide the rotation. And with the other action, I can decide the acceleration, the velocity. And then the last one is the pink one, which is a car. So with the car, I cannot decide the rotation when the car is stationary, but I can give a steering angle and an acceleration. So while it's moving, I can rotate it, but I cannot rotate it on the spot. And yeah, the car is like probably the most complex here. And the idea is that we will see all these different models. So this is what it looks like at the end of the notebook, basically, when we will train it. But yeah, going through the VMAS section first. So there is this big VMAS implementing custom scenarios. Here, just some section on installing dependencies. And first, implementing the scenario. Is it big enough? Or maybe I can, yeah. So what you need to do when you want to implement your own scenario is that you will have these abstract functions that you need to implement, which is make the word, where you instantiate your agents, reset the word, observation, and reward. And by defining each of these, we will define your POM-G. So the first one is make word. And in the make word function, you have as input the batch dim, which basically is the number of environments you want to simulate, the device, and the custom parameters, which are the arguments. And you can see here in the first part of the make word function, what we do is we just read from the KWRs, we just read our parameters. So this could be parameters like number of holonomic agents, number of differential drive agents, number of cars, number of obstacles, and so on. So this is really where you just configure your scenario. After you have configured the scenario, you can create the word. The word is this like object, Python object, and it will just need to take the number of environments, the device, and some physical parameters, like how many times do you want to sub-step the simulation, what is your delta t, what is your gravity, what is your drag, your friction. Here we mostly leave defaults for these values. But yeah, here is where you would customize the properties of the physics. And then you add the agents. So here we first define a list of colors that we want our agents to take. But then like we just do for I in the number of agents, we just choose the color for that agent. We add the sensor. So this sensor is LiDAR. So this basically is what they will use to perceive other agents. And you can tell this sensor only pick up other agents. So I only want other agents to be affected by this sensor. And you can give it how many rays you want, what is the distance, and so on. And then you can instantiate each of the agents. So for the holonomic agents, you will say, okay, name, holonomic, collide, yes, this is the color, this is the action I want to render, this is the sensors I want the agent to have, this is the shape with the radius. In this case, this agent will be a sphere. And then these are some parameters for the actions, like what are the ranges, what are the multipliers, and the dynamics. So the dynamics is basically, in this case, what will define your action space. So in this case, you say dynamics is holonomics. So these agents will have 2 actions, which is force X and force Y. It can move any direction in 2D. And then similar thing for the differential drive. The only thing that changes here is dynamics will be differential drive. So this one defines that the actions will be one forward velocity and one angular velocity. And same for the car. The only difference here is that now the model is this kinematic bicycle, which is what we use to approximate a car kinematics. And here the 2 actions are the velocity and the steering angle. And yeah, here just some tensors to store the rewards. Like here we just store the rewards for positions and collisions. And then we just call word.addAgent. And then we do the same for the goal. So for each agent, we spawn a landmark, which will be non-collidable, representing its goal. And maybe it's worth noting that in VMAS, so you have this concept of an entity, which is something that lives in the physical world, and it could be either a landmark or an agent. The difference between landmark and agent is that the agents can take actions, but both of them can be collidable, rotatable, movable, and so on. So they have similar customization. So in this case, we have landmark, which is another sphere, just non-collidable. And we add this as well. And then we add obstacles, which are also landmarks, but in this case, collidables. So you just will be penalized for colliding into them. And again, we store some rewards, some tensors, just for safekeeping. So this is basically what was the make word function. Here we just say we instantiate the agents, we instantiate the landmarks, and we get our simulator ready. The next one is the reset function, and here is probably where it's best to talk about what vectorization is. So normally you would have, your position is a vector of 2D. If you're in 2D, is x and y, and this is how normally you represent a position. But in VMAS, because of the vectorization, the position will be a vector, or in better, a matrix of shape number of environments, comma 2. And this means that each of these rows in this matrix will be the position of this agent in one of the environments. You know, the first row is the position in environment 0, the second row is the position in environment 1, and so on. So here, when you're calling the agent.state.position, what you have is not just a 2D vector, but is this matrix that has the position in every single environment. And why is this? Because if you have also a velocity that has the same shape, then you can do something like this, position plus velocity times delta t, and it gives you the next position. But this computation, if it's done on only one environment or on n environments, has the same costs on a GPU. So this is the idea why we keep all these environments together in the same tensor, such that we don't pay any extra cost for having more environments. And usually you don't even notice it, right? If I do like pos plus vel, you won't even notice what is their shape. But one place where you notice this is in the reset function, because some environments might be done before others. Let's say that in one environment the agents already arrived at the goal, but in the other they didn't. So when you are asking, when the task is completed and you're asking the word to reset, you have to tell it what environments you want to reset. So when you implement this reset word function, you have this input which is env index, which is basically when it's none, it means reset everything. And this is simple, just reset all the environments. Otherwise, it's an index of one environment that you need to reset. And you just need to reset that and keep the others untouched. And in this function here, we are using a utility which basically allows us to spawn the entities at random. So we just give it the agents, the obstacles, and the goals. And this function will just basically spawn them at random positions within our desired bounds. And it already takes this index, so it will implicitly do the resetting of only one or multiple. And then the other thing that we're doing is that for each agent, we're computing the distance to the goal, because this is something that we want to store for later for computing the reward. And here is where you can see the difference. If the environment index is none, you have to compute this distance for all environments. Otherwise, you can just compute it for the environment that was requested, because this is the only one that's changed. Yeah, if there are any questions, feel free to block me. Then the next one that we want to implement is the reward. This is probably the most crucial in RL. Basically, we have to incentivize our agents to go to the goal. And we will do it using 3 rewards. One is just like proportional to the distance to the goal. The other one is like a sparse reward that they will get only when they all succeed at the task. And the other one is a penalty for collisions. Here there is quite a point to be made where just thinking about the reward for incentivizing agents to go to their goal. So you might think that a good choice is something like the distance. If I give the agents like the negative distance to their goal, they will want to maximize this and so basically get closer to the goal. But this is a bad choice. And yeah, there is a chocolate if you can tell me why, and you didn't read the notebook before.
Because it may be different for different environments. So every environment you have different distance to the goal, so it's hard to normalize.
Yeah, but you're not normalizing, right? You're just saying you need to minimize this. So if you're spawned like at 1 million kilometers away or 1 meter away, you will still, like, if you minimize that distance, you will still go towards the goal, right? But what's the other problem with, like there is a problem regarding to how it actually is this distance, but it's not this one.
Maybe obstacles that will like limit your way to.
Oh yeah, but obstacles is another term in our reward. So this is just something, a reward for you to go to the goal, and then you will have a penalty for colliding as well. So for now, you can imagine there are no obstacles. But yeah, specifically in this case where you're like, maybe in one environment you spawn 1 million kilometers away, and in one environment you spawn like a few centimeters away. Can you think why is a problem if you use the absolute distance as the reward? Like,
coffee, not chocolate.
coffee chocolates. Like one thing that will happen is that you will be rewarded in different ways. So like what you actually want to achieve is that if you go towards the goal, you get a reward. But this reward should not be different if you are like a lot of meters away or pretty close to it, because a step towards the goal should have the same value independently. So the problem is that it cannot depend on the absolute distance, because then you will have a huge penalty when you're very far from the goal and a very low value penalty when you're close to the reward. So if you're coming from 1 million kilometers away, it will be very important to do the first steps towards the goal. But when you reach like proximity of it, the reward is so small and so trivial that compared to the ones you just saw, it's fine. You don't need actually to reach the goal because the scales are so different. So what we actually use instead of the negative distance, which by the way was the ones used for MADDPG and all that, so like a lot of people make this mistake, is that instead we will use the relative distance to the goal. So I take, and this is written here, let me just grab it. So I take my previous distance to the goal and I subtract my current distance to the goal. So now if I take a 1 meter step towards the goal, it doesn't matter if I'm 100 kilometers away or just nearby it, I will be rewarded in the same way. And proportional to how big is my step. So this is the position reward, and then there is also a final reward that basically when all agents reach the goal, you will receive this sparse signal. This is not super fundamental, but you can even imagine just having these. Like it would be harder to learn, but this should be enough. And then we will have penalties for agents colliding. So here is just a collision check where like if you're colliding with other agents or colliding with obstacles, you basically are penalized. And the final reward that each agent gets is the sum of this position reward, this final reward, and this collision reward. And the collision reward is always local, the final reward is always global, and here for the position reward you can decide whether you want to share this or not, and this will have implications on the learning. Yes, and then when it comes to observations, here we basically just define what we want the agent to receive when it's taking an action. So here, this is just a dictionary of tensors. So we say we want some obs, and this will contain the relative position to the goal. Very important, because without this, the agent doesn't know where to go. The relative position to the obstacles, very important, because the LiDAR is only used for other agents, but not for obstacles. So you need to know this to avoid the obstacles. And then you will have the LiDAR readings from your sensors. And then also your position, your velocity, and for the agents that also have, they're not holonomic, they will also see the rotation and angular velocity. And so this makes the observations heterogeneous because the agents, the cars and the differential drive will have more observations. The done is very simple. You're done when everyone reaches the goal. So we can have this, just returning this thing. And then there is an info function, which basically you know, if we're just logging the reward, we want to know how it's composed. You know, how much of it is avoiding collision, how much of it is position, how much of it is final. So in the info function, you can log like more granular things. For example, like your collisions and so on to keep track of these throughout. Extra render we won't see just now. But yes, what it's fundamental is now that you have all these functions implemented, then you can make the environment.
I have a question.
Yeah.
If the done were set where you're only a proportion of the agents reaching the goal, would that be an option, or? Because the
Would you
policies
give
are
them a reward for that?
Well, the policies are homogeneous, but I'm just wondering if you want to scale the system and train with thousands because you want that kind of interaction going on. But obviously having a done label, which is only done when 1,000 have reached their goal, is much harder than if you have, say, 900 reaching their goal.
Yeah. Like if we actually have a done label where 1,000 reach the goal, what we do is that there will also be like a number of steps. So usually it's either you're done within 100 steps or you're done anyway. So we also cut it at fixed length. So you can put the done anywhere you want. The thing is that it should be significant to what you experienced before the done. So yeah, I mean, if it was very difficult to get to the done state, the time limit will kick in before that anyway. So when you're making the environment, you just have this function called make environment, and you just pass it your scenario, the number of environments you want, the device you want to simulate on, and the seed. These are some default values, like for example, VMAS can be used with both continuous and discrete actions. You can choose. You can pass this maximum number of steps, which is what we just said, which is these will be used together with the scenario done to determine when it's done, and then other parameters. And then in this function, you can pass anything you want to pass to your scenario, which is the things we defined in the make word function just a second ago. So this is where you would configure it. And here in the notebook, I just explained some of the shapes of the stuff, the step. You know, this is the core function of an environment. It's as you will have seen in RL, you have this env.step. You pass as input the actions, and you get as output the observation and the rewards. So this is very similar to other RL libraries. Yes. So this section just explains what this means for each of these quantities to be a tensor. And then there is a function called useEnvironment, which basically what it does is you make the environment in its first few lines, and then it will do like a number of steps, where for each step it picks a random action, and then it passes the random actions to the environment, and then gathers a frame called m.render. And so with this function, you can just say, roll out my environment for 100 steps. It will take 100 random actions. And we can do this. We do this in the notebook, and you can see that at the end we get something like this. So this is 100 random steps in the environment. You can see like we have all the components we defined, the agents, the lidars, the obstacles, but right now they're basically clueless. These are just random actions. So I mean, it's good to benchmark that everything works, but the next step is to train them and actually like optimize for the reward. Yeah, so going back to this, I left some extensions in the notebook if you want to play with this. Maybe one question is, if we see in this scenario, like how can we now make it harder? Do you have any ideas how we can make it more difficult to solve?
Well, increase the number of agents or obstacles.
Yes. Yes. Increase the clutter. Yeah.
Time limitation?
Sorry?
Time limitation.
Time limitation. Yeah, I mean, if they are constrained, like if they at the best they could do, they can reach it in 50 steps, and you just give them 50 steps, then it will be very much super harder to see that. Yeah, so that's also. Other ideas?
Fewer LiDAR sensors?
Fewer LiDAR? Yeah. Like few arrays to avoid the, yeah. Yeah, there are actually like infinite ways to make it harder. Like these are some that I wrote. I think fewer LiDAR is less observations, more clutter is more agents, more dynamical constraints. So there are many ways. And some extensions that you can try if you want to play with VMAS is that you can try to add a LiDAR for obstacles and remove them from the observations. You can try to script on one of the agents. So instead of making it a learning agent, you can write a rule-based controller to just control that agents. And RU, the very advanced extension, would be like spawn two agents at a fixed distance, link them with a physical joint. Now they will have to travel together and avoid collisions in this n-body shape. Very hard to implement and very hard to train. So this is advanced. Okay, so we're more or less on time. Any questions about the simulation part? Okay, why do we need training? It's the same question as why do we need simulation?
No wrong answers here.
Yeah, really. Well, I can start giving some background and then maybe you can tell me if you find a few points. But one point is that the centralized sequential decision making can be extremely hard, and you can solve it with exact solutions, which are optimal, but are very expensive and scale badly in the number of agents, or you can solve with heuristics, which are good complexity, but they lack optimality guarantees. And so learning, at least multi-agent reinforcement learning, sits a little bit in the middle when it can approximate policies through training and efficiently solve new instances, like generalizing. And the way that this helps is in scalability, in hardness, and speed. So scalability is maybe I can solve this optimally for 4 robots, like some of the VMAS scenarios, but can I solve it for 4,000? Or like I might not even be able to solve it for 1 robot if it's a very complex arm or robotic hand that has a lot of degrees of freedom. Then even in that case, I might need already to learn a solution for that because I don't have a real model. And the other one is speed. So the training speed could be arbitrarily long or arbitrarily fast, but at inference time, when you deploy your neural networks, the inference is usually very fast. And so the inference time does not depend on the number of robots or something like that. And again, as before, in what is different from single agent, there are more agents and this complicates things. But in practice, some things that are agreed upon is that, well, everyone agrees that execution should be decentralized. So the agents should be able to execute in a decentralized fashion. Otherwise, we're kind of back to single agents. The other thing is that the training could be either centralized or decentralized. And the value functions could be independent or coupled. So these are two things that we saw in the previous lecture, but independent value function, each agent is like running a single agent algorithm, like without considering the other agent as part of the environment. In a centralized critic, the value function takes information from all the agents, and in value factorization is a mixture of the two, where you have independent value functions that then are composed into a global one. And then another dimension is that should the agents share their policies? Yes, no, and this is the parameter sharing question, which emerges only when you have multiple agents. So hopefully we now think that we need learning for our problem, and we kind of know which centralization or centralization we want for architecture. Do we need the library for our research problem? And the thing is that most researchers, maybe including you, code their own training loop. And the process of this is you write your own bugs. It's fast. It's simple and small. It's custom because you just do it for what you need, and it's easy to set up for you. The cons are that you write your own bugs. It could be correct or not. You don't really have a way to say. It's only you. it could be overfitted to one use case. For that reason, it's not parameterizable or customizable. It's not easy to reproduce or benchmark because it's custom, and this leads to long-term costs. So like it's a pain for other people to get in your mind when they need to replicate this work. And usually it's unmaintained and undocumented. On the other hand, using a library, well, the process that it should be tested, it should be parameterizable, it should be easy to change components, and thus like having standard scripts for comparisons. Someone did the work for you, which is a good pro. You don't have to do it yourself, and it should be maintained and documented. On the other hand, they write your bugs, which is more frustrating because not only you have to solve them, but you didn't need to spot them and understand them. The scope could not be aligned with your research needs, and I think this is the biggest cons because the research needs are so varied that it's difficult to find something that fits your exact use case. So it's really important to understand what a library can do for you and they cannot. And it can be complex and intricate because it has to support so many use cases. Sometimes you have to work with abstractions and object-oriented programming, and if you write your own custom solution, it's easier. Yeah, so I'm curious if where does the audience stand? Like, do you guys usually write your own libraries when it comes to training things, or if you've done machine learning, or do you use something existing? Can I get a hand raise for who uses a library? Okay, and a hand raise for who prefers to code the stuff themselves, the training loops. Okay, it seems like a majority is library oriented, which is good. We are talking about the library. But there is something in the middle, okay? So there is also Torch and Jaxu, which is like library of components. And everyone thinks this was a good idea because no one wants to re-implement differentiability and all that basic operations. And there is an open philosophical question as well, which is, do researchers have their incentives aligned to make these open source versus individual scripts a thriving environment? And this is something you can think about, and if you want my opinion, you can ask later. But yeah, so other libraries, apart from the one we're going to see today, because there is no one-fit-all solution, so I put some multi-agent and some single-agent RL libraries here. So Mava and JAX-MERL are multi-agent RL libraries for JAX. I mean, if you are approaching JAX, I would check them out. Probably Mava would be my go-to choice between the two. When it comes to Torch, these two, ePyMARL and MARL-lib, are two Torch libraries that were used. Like this was most in the community. This is a multi-agent extension of RL-lib. And these two are single-agent RL libraries, but they are the two more popular ones. So I just put them there because a lot of people customize this for multi-agent use cases. So the focus point is that all these PyTorch libraries here are not vectorized. So you would not be able to use the benefit that we saw before with VMAS in the sense of keeping running on GPU a lot of environments at the same time. But they're all like different studies for different use cases, so there is always a case where they're a good choice. But the ones I want to talk today is, well, first one is TorchRL. So TorchRL is a PyTorch reinforcement learning library. So it was born from Meta PyTorch, and it's maintained there, and the core is that it should be like only dependent on PyTorch. And it tries to keep the PyTorch vibes in the sense that this is not a library where you have like a something.run, but it's more like a library of components. So if you want to pick a single component, like a buffer or an algorithm, like a loss, this library provides that. And the idea is that, without going into much details, there is this one thing, which is called the TensorDict, which is basically almost a dictionary of tensors. But it has some tensor-like properties. So like it could be seen as a tensor itself. And it's useful for containing different tensors. In this case, you have the observation, the action, the done. And in the case they share some like batch size, the TensorDict would also have the batch size. So it allows you to group things according to their batch size. But the main reason why this exists is because it unifies the signature in RL. So you saw before you have m.step equals obs, comma, and you have like a tuple of 5 outputs. Well, with this you don't, right? Because every class will take as input and give as output a TensorDict. So you have a loss, it will be TensorDict to TensorDict. You have an environment, it will be TensorDict to TensorDict, and the same for any component. So this is like the glue and the interface that's used to communicate between stuff, between different components. So the TensorDict and TorchRL provides these individual components, the single loss class, the single environment and stuff. So BenchMARL, the idea is that this is the library. This is something that does not re-implement the RL things, but wires them together in a way that's easy for you to run an experiment. And the few reasons, like the focus of this library is on reproducibility, it's on statistically strong evaluation, experiment independence, and the breadth of over the ecosystem. So over the different choices there were before, like communication, heterogeneity, blah, blah, blah. It tries to allow flexibility around that space. And the idea why it was born is that, well, people were complaining that the research lacked standards. It was just like, SMAC was shown to even like work without any observations, and all the research on that was basically useless. And so people were like, we really need to standardize a bit the system and at least the reporting tools. And so the people proposed these reporting tools, and the idea is BenchMARL hooks onto these tools that generate these plots to basically provide the backbone for running the experiments. Yeah, without going too much details, the core thing is this, right? So you have like run, and then you can specify an algorithm, you can specify a task and a model. If you want to run a benchmark, you can like give a list of algorithms, a list of tasks, and a list of models or something else, and it will run every single possible pairing of these. And you have a lot of choices within these components, and the best thing is that you can mix and match them. So you can choose like, MADVPG, and then you want, CNN with a GNN and then a GRU. You can mix these models in different layers. So some of them are memory models, some of them are graphs. And then you also have these tasks where you have simulators, and for each simulator, a lot of tasks, like the VMAS ones we saw. Yeah, this is basically how it works. You have this, if you run something like this, like run, you give one task, one model, and 3 algorithms. It will create 3 experiments, one for each algorithm. Load the configuration from YAML, which is outside of the Python code base, and then load the configuration into the Python classes, run the experiment, and plot it for you, ideally. Yeah, so just saying there is some 1DB published results on some VMAS tasks. And then, yeah, again, the list of stuff we will see or we will not see that you can refer to later. But yeah, let's jump into the BenchMARL part of the notebook. So here again, some installing dependencies, some recap, some details about adding the task to BenchMARL. It's not very important for this lecture. The first thing I want to show you is like how to configure the library. And we will use, you can use BenchMARL from like a command line interface or from a Python interface. In this case, we use the Python interface. So the first component that we want to configure is the experiment. This experiment contains all the hyperparameter about the run. And we start by calling this get from YAML, which basically loads the defaults into the Python data classes. And then you can override some of these. For example, we override the devices. Here we say how many frames we want to collect before the experiment ends. What is our gamma? What is some parameters for the on-policy algorithm? And in this case, we will use PPO. So like in this case, we collect 60,000 environments, frames. We use 600 environments, each collecting 100 frames from VMAS. And then we evaluate these. Some important things that here you can choose loggers or list of loggers. And the most popular choice is weights and biases, which we will also see. But in this case, we're just logging 2 files. Then the second thing you can do is configure the tasks. So tasks are enum. So you start from something like this, like VMAS task dot, and then you will see a list of possible tasks that are already like implemented. In this case, we go to navigation and we get the parameters of that. And we override this with our parameters for our custom navigation scenario. So we just say how many steps we want. This is like the number of steps before the environment is done, the number of anomic agents, the number of differential drive, the number of cars, the LiDAR ranges. And the same thing goes for the algorithm. So we load the map algorithm and we get its config from YAML. And then here we can override every part of it that we want. For example, what is the parameter sharing? What is the epsilon, the entropy? These are all like PPO related parameters. The model is the neural network that's used for the critic and the actor. So here we are just saying we want an MLP with simple number of cells, layers, activation, and we load an MLP for both the critic and the policy. And now we have all the components we need, right? Because we have defined our models for critic and actor, we have defined our algorithm, and we have defined our task. So BenchMARL is happy just with this. So what you choose is to experiment, and you say task equals the task, algorithm equals the algorithm, model and critic model, and you just call run. And yeah, what I have done is that for the 3 runs, we were going to see like 4 runs, and for this I published on 1DB like what it looks like when it finishes running. So this is what BenchMARL would log from that run. So you can see here, you know, the evolution of the reward over time. And here, for example, you can see the renderings over time. Oh, this is very big. But you can basically choose any training iteration and inspect like what are they doing. Like you would imagine if they're close to 0, they're not like they're just learning, and then as they get better, you can see how they arrive to their goals. Yeah, the car always has more problems because it's very difficult to park. Yeah, so after it's trained fully, you hopefully see something like this, where you can see that the agents are clearly avoiding each other and reaching their destinations. And this is all good. Now let's change something, and something we change is that we will just have holonomic agents and remove the physical diversity. So before we had, you know, a car, a differential drive robot, and 2 holonomic vehicles. These are physically different, so they were in different groups, and they were using, you could have used even different losses or different models for them. But now, since we want to use in a few lines, we want to use the GNN for making the agents talk to each other. This only works when they are in the same group. So we make everyone the same holonomic, and we basically train again. And this is also available on weights and biases. But what it looks like at the end is something like this, where the agents are doing the same task basically. They're holonomic, so they can move in any direction, and they're using these LiDARs to avoid each other. And you can see that they're successfully avoiding each other with the LiDARs, but it's very reactive. You know, it's like they're bouncing almost off each other. So what happens if we disable the LiDAR? Okay, so let's just put the LiDAR range equals to 0. And if we redo all the training, is that we see like the agents are really good at doing the task, but they have no way to avoid collisions, like no way at all. And since there is nothing they can do about this, basically they will still just succeed in navigating to their objectives, but they will be completely blind. So one thing we can think of is that okay, we are not allowed to use LiDARs, let's say, anymore, but we still want to avoid the collisions. So how can we do this? Yeah.
Maybe make them communicate with each other where they're heading.
Yeah, that's right. Chocolate? You have preferences? Hazelnut. Yeah, so we make them communicate, and the idea behind this, I think we will see in the next lecture more in detail. But the idea is that the agents, if we let them share information or observations among agents close by, this is quite good for some reasons. So the first reason is that you don't need to communicate with faraway agents in this task, because if you need to deconflict trajectories locally, you won't care about someone, you know, maybe a kilometer away from you. So it's good that we build this communication graph based on their positions. And the other thing is that you can still train in a decentralized way. You know, you just need to access information from the neighborhood and nothing global. So even with this communication paradigm, I wouldn't consider it centralization. And so execution and training can be still decentralizable. The practical way we do this is the GNN. Maybe you will see more details about in the future, but what the GNN is able to do is that it's like a graph, and so the policy is a graph where now the agents can communicate and have edges between each other, and these edges contain features like relative positions, distance, and relative velocities. And these features are crucial to avoid each other, because relative position will tell you how far you are. So when you are in BenchMARL, the only thing we need to do is to replace the model. So the algorithm and the task are fine. We just need to add the GNN to our model. So here is what we do in this section. It's like GNN config. And here we tell the GNN how we want the topology. So you can say full topology, and everyone will be able to communicate with everyone at all times. But in this case, we say we want to build the topology from positions. So, and we provide a radius for building this. So I want to only speak with people 2 meters away from me. And then we provide a class from Torch Geometric. So Torch Geometric is a library of GNNs. And you can provide any class from this library here and plug it in and customize it with the arguments. In this case, yeah, we add this residual collection, and we use an attention network. So this is similar to a transformer, saying the agents will have a weight on each edge depending on how much attention they pay to that agent. But this is just details. Like we just care that they're able to use an architecture that has edge features. And then here we tell, where do we find the position key? So in the observation that we made before, in the observation function of VMAS, what was the name of the element of the dictionary that contained the position? And the name was pos. Position feature is 2 because it's 2D. Velocity as well, 2D. And we exclude the position from the node features because, again, this is a point that we don't want to be conditioned on the absolute position of the team. Like if we translate everyone just a little bit, the output shouldn't change. What actually we care about is the relative positions between each other. So this little line at the end makes it the problem translation invariant. Yeah, the task, now the only thing we change with the task is that we tell also VMAS what is the communication radius. And so VMAS will be able to just plot lines to show us how the edges communicate. And we retrain. And it looks something like this, right? So no LiDAR, no LiDAR, but communication. And you can see that it's even better than with LiDARs, because with LiDARs it's very reactive. In this way, they could do some kind of planning, or at least communicate from a little bit far away to organize with a little bit more anticipation. Yeah, and so if you go to if later you're curious and you want to go to the weights and biases, you can have these 3 things together, next to each other. You can see, like the LiDARs, the non-LiDARs, and the communication. And what's cool is that, like, let's say we want to look at the collision reward. You remember when we coded VMAS, we said with info, in the info dictionary, we added this collision reward thing. So this was also logged, and you can see that when you have a GNN or when you have a LiDAR, the agents start learning to avoid collisions, but when you have no LiDAR, this will never improve. And so it's just a confirmation of what we said, and the same thing for all the other reward functions. Yeah, and you can inspect a lot of things from here, right? So you can inspect like clip fractions, entropy, KL approximation, loss objectives, all the training related parameters. Yeah, and this is basically was a gist of how to train something in BenchMARL. Again, extensions. Here there are more. If you're curious and if you want to use BenchMARL, if you want to become proficient. Beginner, you can just change the algorithm. So we use MAPPO. You can choose any other algorithm you want. If the algorithm you choose only has discrete actions, like Q-learning-based algorithms, it will automatically change the VMAS setup to use discrete actions, because VMAS supports both. You can change the model, for example, add the memory layer. If you have the GNN and a memory layer, can they plan? Can they remember, like, from previous interactions, and can you get better performance? This, of course, will come at the cost of training time. try to train the agent to the share reward now instead of individual rewards for going to the goal. And this is the more easy things. The more intermediate ones, you can disable parameter sharing. Think about the implications of that. See the implications in your trainings. The other one is MAPPO uses the centralized critic. So we saw this critic that takes input from all agents. And it concatenates them. So basically it will be dependent on the order. But BenchMARL has a model called deep sets, which is used to encode a set. So it's not dependent on the order of the input. So you can try to use that for the model of the critic instead and see if you get better generalization. Or you can try using different algorithms and models for each group. And in the hard area, you can set up a curriculum learning in the sense like through callbacks, you can slowly anneal the dense reward that the agents are receiving and at some point just leave the reward for going to their goals. If we think about the scenario before where they have to do it in X time step and there's a very big constraint, this might be a way to help them do that. And the other one is you can implement the GPPO algorithm from a paper that we saw in the previous lecture. This is basically easy in BenchMARL because you can recover a lot of the existing algorithms from just a composition of these models and algorithms. So for example, this would be IPPO plus a GNN for the critic, a GNN for the actor. The only difference you need is like share parameters between the actor and the critic. And here is a pointer on how to do that. But yeah, it's very easy to retrieve new algorithms. So if, for example, you want to try GPPO, but instead of PPO, soft actor critic, you can do that. Yeah, and basically that was it. This is just a recap of everything. So this is exactly the same pipeline we've been through today. These robots were simulated in VMAS, trained in BenchMARL with the GNN model, which is also GATV2 with attention weights. And then deployed just to the real world. But really, this deployment was just take the BenchMARL checkpoint and run it on the robots. And here is again a navigation task. They're all autonomic and they don't have lidars, and they just need to go to their goals by the conflicting collisions. And they never saw this specific setup in training. This was customly created because in training, like how we set up the task is the robots are randomly spawned and the goals are randomly spawned, and this is something called domain randomization. So if you have this set up, then you can choose any specific instantiation of robot and goals, and they should be able to do it as long as it's within the distribution you use in the spawning. Yeah, and that's it. Hopefully, yeah, 10 minutes past 12, we should be in line.
Yeah.